Hello, today we are going to learn how to create an advanced SLURM script. In a previous video, we explained how to write a simple SLURM script. The link to that video is down below. I suggest that you check it out if you are new to the cluster. In this video, I will explain how to use other, more advanced SLURM directives to have better control over the jobs that you want to submit to the cluster. I will explain how to create job arrays, specify the working directory of the batch script, how to create dependent jobs. I'll add some comments about SLURM environment variables. And finally, I will explain how to receive email notifications. Let's get started with job arrays. Job arrays will allow you to create multiple jobs using a single script when you want to run the same set of commands on the data of different subjects. These jobs will run parallel on all subjects. The best way to understand job arrays is through an example. First, I'm going to give an example of a situation in which I would like to use a job array, and then I will show you how I would write a SLURM script to achieve what I want to do in the cluster. Imagine that I have a project that consists of 20 subjects. They are characterized by a unique ID of the form subject 1, subject 2, subject 3 until subject 20. In the Scratch directory, which is where I will save and submit the SLURM script, I have a text file called list.txt. It contains the list of subject IDs, one ID per row. I also have one input file per subject, which is a text file with the name of the corresponding subject and other personal information. Here we have an example of what that input file looks like. I want my script to read each line of the corresponding input file and write that in a separate column of a CSV file. This will allow me to run statistics or tests on the data. So, the output file will contain one line per subject, and each line will contain 5 columns with the personal information of the corresponding subject. Here we have an example of how we would want the output file to look like. The output file most probably won't be in order, because each of the 20 processes generated when we submit the job array will write to the same output file, but the order of the lines will depend on the timing when each process writes the output information, which is random. When I run the script, which I will show later, the first line of the output file corresponded to subject 1, the second line to subject 2, the third line to subject 19, the fourth to subject 11, etc. This is the SLURM script that we created on the previous video. We will edit it to create the job array that we need to accomplish what we want. If you don't understand the content of this script as it is, I suggest that you check out our video on how to create a simple SLURM script before you continue with this video. Now let's get started by editing the header. We will leave all the directives that request resources as they are, because each job from this array will still run on one task and use only one CPU per task. Remember that here you must replace PINet ID by the network ID of your PI and not with your own network ID. The resources that you specify here are not the total amount of resources, but the resources that each job of your array will have. That's why we don't request 20 tasks or 20 CPUs. We request only one task and one CPU for each job of the array, even though your array will have 20 elements. We'll change the job name to my job array now. And we'll edit the name of the output file. Instead of using %J for the job ID, we will use %A, and we will add %A for the array index. So, if the job ID is 12345, then these will be the names of the output log files for each element or subtask of the array. My job array, which is the name of the job, dash 12345, which is the job ID, dash the corresponding index dot out. Since the resources we request here are not for the whole array, but for each subjob of the array, we are requesting 20 gigabytes of memory in total instead of 1 gigabyte, because each of the 20 subjobs will have 1 gigabyte. Even though all jobs must have the same initial options, it is possible to change some of these after the job is executing using the scontrol command. If one of the subjects, for example, has heavier data and requires more memory or wall time, you can write us requesting to change those resources for a specific element of the array. Now we can add the most important, the array directive. This can be done in a few different ways. If we want to run the script on all 20 subjects, we will just write --array equal 0-19. Remember that in many programming languages, including Bash, array indexes start with 0 and not with 1. So if we have 20 subjects, the indexes of the array will go from 0 to 19 instead of 1 to 20. If we want to run the script on only the first 5 subjects, we will write --array equal 0-4. If we want to run the script on only the last 5 subjects, we will write --array equal 15-19, because the subjects in indexes 15 to 19 are the last 5. If we want to run it on every other subject starting on the first one, which has index 0, then we would write --array equals 0-19:2, meaning every 2 indexes. This could be useful if, for example, you have your subject list file is organized in a way that each subject has 2 sessions, and you just want to analyze the first session. So you want to skip every other line in the file, which are the lines with the identifier of the second session. This will only run on indexes 0, 2, 4, etc. If our array is very large, for example, it has 100 subjobs, we will want to limit the number of jobs running at a time. Otherwise, you will reach your limit of number of jobs that can be submitted and won't be able to submit any more jobs to the cluster. So, let's say we want to run 10 jobs at a time maximum. We can then add a %10 at the end of the directive, like this. Each job from the job array will have an environment variable called SLURM array task ID. This variable represents the index value of the current job that is running the script. We will use this variable to know which subject ID we extract from our list of subjects. Let's now write the actual commands that will be executed on all subjects. We're first going to add this flag, -e, right after the header with the sbatch directives. It will make the program exit as soon as it encounters an error. Otherwise, the program will continue to execute after an error, potentially producing wrong results. For example, if one of the subject files doesn't exist, we want that job to fail instead of writing an empty line on the output file. It's a good practice to use this flag in every SLURM script and not only when using arrays. In this line, where the red arrow is pointing, we read the content of list.txt and save it in an array called subjects. In this line, we obtain the subject ID for the subject that is going to be processed by the current job from the array. In this script, I am creating an array of 20 jobs, and the variable SLURM array task ID will have values from 0 to 19. For the subjob where variable SLURM array task ID has value 5, variable subject ID will have the value of the element on index 5 of the array of subjects. This will be the 6th element of the array, since indexes start on 0. So the subject ID that will be processed here will be subject 6. In this loop, the script reads line by line the content of the input file for the corresponding subject. And finally, we save the information that we obtained from the input file into one line of the output file. As I mentioned before, just because this is the 6th element of the array, it doesn't mean that it will write in the 6th line of the output file. Because all subjobs are writing into this same file, they are sharing a resource. And we don't know the exact timing at which each process will have its turn to write. In this case, this process was one of the last ones to save the result. This is a very simple example with the purpose of illustrating how arrays work in SLURM, but you could write a similar script to do some complex processing on heavy data of different subjects. Now let's see how to specify the working directory. You can do this using chdir. With this option, the log file as well as any files with a relative path will be saved here. Any input files with relative paths will also be searched from this location. In this example, the log file and the output file out.txt will be generated in Scratch G my group my dir. Next topic is dependencies. Usually when running a processing pipeline, each step of the pipeline will run on the output of some other previous steps. And those previous steps will in turn depend on the output of other steps. In this example, I have an imaginary pipeline that consists of 5 processing steps. Steps 2 and 3 cannot run until step 1 has finished successfully, because they use the output of that step. Step 4 can't run until both steps 2 and 3 finish running successfully, because it uses the outputs of both steps. And the final step, step 5, can't run before step 4 finishes running. This is what we call dependencies. Step 1 is a dependency of steps 2 and 3. Steps 2 and 3 are dependencies of step 4, and step 4 is a dependency of step 5. To manage dependencies, you can use the SLURM option -- dependency. In this example, the dependencies had to finish running successfully, but your pipeline might have dependencies that required a previous step to finish running, but it might not matter if it finished with or without an error. Or you might want a step to run if a previous step fails. I will explain in a bit how to specify the type of dependency. Your job can have any number of dependencies. If a mandatory dependency job fails, the dependent job will never run, even if the dependency is requeued. If your job requires that all dependencies terminate, you will divide the job IDs with commas. Whereas, if your job requires that any of the dependencies terminate, you will divide the job IDs with quotation marks. One must divide the type of dependency and the list of job IDs by a colon. The type of dependency can be one of the following: after any, after core, after OK, and after not OK. Let's see how each of these type of dependencies work. The type after tells the scheduler to run the job after all if separated by comma or any if separated by interrogation sign of the specified jobs start or are cancelled and the amount of time in minutes from either event happens. If there is no time, there is no delay. In this example, we want the current job to run after job with ID 11111 starts or is cancelled. and 3 minutes have passed after either event. And after the job with ID 22222 starts or is cancelled, and 5 minutes have passed after either event. The two dependencies are divided by comma, so both must become true before the current job starts to run. Let's look at another example for this type of dependency. In this example, a couple of things changed with respect to the previous example. First, the dependencies are separated by quotation mark instead of comma. So this job will start running as soon as any of the dependencies are met. Second, the second dependency has a delay of 2 instead of 5 minutes, and the first dependency doesn't have any delay. So as soon as job 111 finishes or is cancelled, this dependency is met and the job can start running, unless it already started running because the job 22222 had already finished and 2 minutes after it finished had already passed. The dependency type after any tells the scheduler to run the job after any of the dependencies have terminated, with or without an error. Here we divide the job IDs by columns. The dependency type after core tells the scheduler to run the job after all if separated by comma or any if separated by interrogation mark of the dependencies have successfully terminated. The dependency jobs don't need to still be active at the time of submission of this dependent job. They could have already finished. The dependency after OK tells the scheduler to run the job after all if separated by comma or any if separated by interrogation mark of the dependencies have successfully terminated. But the dependency jobs must still be active at the time of submission. After not OK tells the scheduler to run the job after all if separated by comma or any if separated by interrogation mark of the dependencies have terminated with an error code. The dependency jobs also need to still be active at the time of submission. Let's see an example of a pipeline in which we would use different types of dependencies. In this example, step 2 and step 3 should run if step 1 finishes running successfully. If step 1 fails, step error 1 should run instead. Step 4 should run only if both step 2 and step 3 finish successfully. That is, if there are no errors in any of the previous steps. If step 2 or 3 fail, then step error 2 should run. Let's see how we would write the header of these files and how the submission and output would look like. This is the code of the first step of our pipeline. In this case, it should run without any errors. The script just prints the time when it started running in a file called out.txt, sleeps for 5 minutes, and then prints the time when it wakes up. This step has no dependencies, so we don't add anything to the header. After we submit the job, we need to take note of the job ID, since this job is a dependency for other jobs and we'll need to include it in their header. This is the code of step 2. To the left, we have the header, and to the right, the instructions. This script should also complete with no errors. It prints the start time to a new output file called out2.txt, then reads each line from the output file of the previous step, adds some additional strings to each line, and prints that information into out2.txt. Finally, it prints the time when the script finishes running. As you can see, we have added a dependency line to the header of the file with the job ID of the previous step. Because the type of dependency is after OK, this job will only run if the previous one completed with no error and should be submitted before the previous step finishes running. This is the code of step 3. To the left, we have the header, and to the right, the instructions. This script should also complete with no errors. It basically does the same thing as the previous script, but the string that it adds to each line of the input file is slightly different. We have added the same dependency line to the header of this file with the job ID of the previous step. Now we submit both jobs and save the job ID to be used in the header of step 4 and the step error 1, which have these jobs as dependencies. As you can see, they did not start running immediately. The status is PD, which means pending, and the reason for not running is dependency, because it's waiting on a dependency. This is the content of step 4. In the left, we have the first part of the script, and to the right, the second part. As none of the previous jobs are expected to fail, this one should start running as soon as both previous jobs finish running and should also complete successfully. This script just prints all the lines from the output files of step 2 and step 3. As you can see, we added a dependency line to the header of the script, similarly as with the 2 previous jobs, but here we included both jobs IDs divided by a comma. With this, we are indicating to the SLURM scheduler that both of these jobs must finish successfully before attempting to run this one. The same as with the previous 2 jobs, it did not start immediately, as this job is also waiting on some dependencies. After step 1 finishes running, we should see that the 2 subsequent jobs start running and the last one is still pending. Let's now see the code of those jobs that should run if something fails, although in this case they won't run unless we edit some of these scripts causing them to fail. This is the content of steperror1.sh, the script that should run if step 1 fails. It just prints the time it started running and that there was an error. The code of steperror2.sh would have the same header except for the job name and the job ID of the dependency. Let's see what the output files of each step look like. Step 1 just outputs the start and finish time of the job. The execution time was 5 minutes, since all this script does is sleep for 5 minutes. Let's remember the finish time. It finished executing 1 minute before 1:36 p.m. The following jobs should start running at this time or after. This is the output of step 2. It did as expected. It started running exactly when the previous job ended and printed the content of the previous output file with some additional comments. All this took less than a second to run. This is the output of step 3. It also running exactly when step 1 ended. Finally, this is the output of step 4. Since step error 1 and step error 2 never ran, we don't have an output file for those steps. Now you have a very useful tool at hand to run your pipelines. Let's look now at environment variables. When a job starts, some variables will be set to certain values depending on the options that were defined in the header of your file. You can use these variables to get information about your process. To obtain the full list of environment variables in SLURM, you can visit the link provided here. I strongly suggest to look at this link because you might be able to obtain information about your job that you didn't know of. For example, if you wanted to know which nodes were allocated to your job and the number of CPUs available to the job in each of these nodes, You could use the following variables to print that information: SLURM job name nodes, SLURM job node list, and SLURM job CPUs per node. Let's look at email notifications. You can choose to receive notifications about any change of status in your job by email. Before using this option, be aware that if you have a lot of jobs running, you could end up receiving many emails. And also be aware that you could also monitor the status of a job in the command line with the command SQ, which we have seen in previous examples. You first should specify the type of notifications that you want to receive. Multiple values may be specified in a comma-separated list, but the most common ones are: begin, to receive a notification when the job starts running; end, to receive a notification when the job finishes running; fail, to receive a notification if when the job fails; and time limit _90, to receive a notification when the process has reached 90% of the hold time. This could be very useful for a very long job that you're not sure if it will hit hold time and that might need some extension. Another directive that can be used to receive email notifications is mail user, which is just the username or email of the user who should receive the notifications. If this is not specified but the other email directive is present, then the emails will be sent to the user that submitted the job. That was all. Thank you for listening, and I hope that you learned a lot. I will see you in future videos.